Hey friends, welcome back. Previously in this series, I introduced the background and motivation for this project. We went on a whirlwind tour of knitting machine history, and then my hands went on a bit of a separate detour to demonstrate how I knit a sock on a simple circular sock machine. Today, we're going to look a little bit more closely at the design process for my own flatbed knitting machine system, the reasoning behind the choices I made, for better and sometimes for worse, the constraints that influenced the design so far, and a few ideas for a longer-term feature roadmap. Before I dive into it though, a couple of quick reminders. This is a personal project, not a product. It's a work in progress still, and I'm happy to share what I've done and what I've learned so far so that others can try it out as well if you want. But I can't guarantee that it will necessarily meet your needs as is, or that I'll ever succeed in adding particular features that you may want. I did lots of research and lots of hands-on experimenting, but I don't consider myself to be necessarily a knitting machine expert, and I'm certainly not a mechanical engineer or an industrial designer. This is absolutely not the final word on how a knitting machine can or should be designed. It's just my approach based on my experience and fueled by curiosity and stubborn enthusiasm. But with all that said, I hope you'll find it useful, inspiring, or at least entertaining. Before I could start printing parts or even start making sketches, I figured I should sit down and think about what I wanted my knitting machine to be able to do. That might sound like a simple question. Okay, well, I wanted to knit, obvi. But knitting encompasses a pretty huge range of techniques that can produce wildly varying fabrics and final products. Plenty of these techniques are achievable on all but the most rudimentary machines, if you're willing to do some hand manipulation. But that hand manipulation can be a lot of work. It can be honestly a bit discouraging to look at, say, a beautiful ribbed sweater dress design and be like, God damn it, I'd have to relatch every single one of those little f***ers by hand. So ideally, the machine could help me do some or all of these things. Or at least not get in my way. Spoiler alert, so far I've only managed to tackle a couple of these things, sort of, but we're in this for the long haul. Now, I'll talk more about designing features in a bit, but even if I ignored all of those different techniques, even if I thought the main course of what I plan to knit would be mostly vast tracts of basic, boring stockinette, I still had a pretty important fork in the road when it came to what types of projects I wanted to prioritize. Yarn weight. So this might go without saying, but not all yarns are suitable for every project. A fluffy, chunky yarn might be a good pick for a big cozy sweater, for example, but that same yarn would be pretty impractical for everyday socks. What might be slightly less obvious is that not every yarn is suitable for every knitting machine, or perhaps more importantly for the purposes of this discussion, not suitable for every knitting machine needle. Now, in hand knitting, there tends to be pretty fine gradations between needle sizes because the diameter of the needles has such a direct impact on the size of the stitch that gets formed, which in turn determines the gauge and hand of the fabric. This isn't exactly the case for the latch hook needles used in domestic knitting machines. Instead of changing the physical size of the needle, the tension on any given machine is primarily adjusted by controlling how far the needles are allowed to travel. In other words, how long a loop they pull through when they pick up the yarn. Depending on the machine, there are other factors that can influence the final gauge of the fabric as well, like how much tension is placed on the yarn feeding in, as well as how much weight is attached to the fabric coming out. Another very important consideration is the spacing or pitch between the needles. Generally speaking, you're going to want a machine with more space between the needles for heavier yarns and needles a little bit closer together for finer yarns. So given all these considerations so far, theoretically, you could knit a pretty wide variety of yarns without having to actually change needles, although in practice you might have to switch machines to achieve a different pitch, and that other machine is probably designed around a different type of needle. We'll get to that. But at the extremes of that range, you might find that you just don't have as much wiggle room to fine-tune the results you get, and those results might not be as reliable as if you had stuck to yarns that are well within the needle's comfort zone. As we push into thicker and thicker yarns, the hook may not even be big enough to comfortably fit around the entire strand, resulting in split stitches or damaged yarn. And the needle may not have enough travel distance to pull a long enough loop when forming new stitches. Okay, so why not just start with the roomiest needle we can then? Well, then you might end up with problems at the other extreme. A larger hook requires a large enough stitch to get its head through easily. And with the ideal gauge for finer yarns demanding smaller loops, this could be a struggle. While you technically can knit these finer yarns with the bulkier needle, just like you could knit fine yarns with a large needle by hand, the stitches may be looser than really recommended, and the resulting fabric then might not have the characteristics you're looking for. Anyway, this all left me with a little bit of a dilemma, because most of the yarn in my stash was either very lightweight yarn intended for socks, or worsted weight and heavier, with almost no middle ground. And those also seem to be the most readily available and affordable yarn categories that I could access locally. Worsted seems to be right on the cusp of what a standard gauge machine might be able to handle on every other needle, depending on the specific yarn. But a bulky gauge, with its bigger hooks, is definitely a much more realistic fit for those yarns. So given this compatibility breakpoint, which needle should I choose? At this point, I'd love to tell you all about how I dug into the market research on the popularity of different yarn weights, or how I calculated that I'd get way more bang for my buck out of the machine using it to knit the thousands of superfine stitches in a fingering weight sweater, or how I stared deep into my own soul and realized that throughout my multiverse of hobbies, my needlecraft origin story always involves being bitten by a radioactive desire for really, really tall socks. And those things would be true, but if I'm being honest, the needles I settled on were the ones that were the easiest to find at an accessible price at the time. Would I choose differently if I were starting again, knowing what I know now? Maybe, but I had to start somewhere. So let me introduce you to the star of our show, the standard gauge latch hook needles compatible with the Brother KR830 or KR850. Now these are actually ribber needles, but for our purposes, that shouldn't matter. If you haven't already picked up on it based on the last several minutes of my rambling about needles and how they interact with the yarn, these guys are pretty darn important, and I'm going to take a moment now to stress, probably not for the last time in this series, you cannot pick up any random available knitting machine needle and expect this design to work for you. I'm not going to say it definitely won't work with any other needle, but as we're about to see, this design is rather precisely tailored to these measurements. For example, here I have a different standard gauge needle made for silver reed machines. Even though they are both standard gauge and they look very similar at first glance, the dimensions are clearly very different when you examine them side by side. This difference is even more obvious when we look at something designed for a larger gauge machine. For example, this LK150 needle. Unfortunately, this means that there's not a simple parameter or two that you can tweak to get a true bulky gauge version of this yet. It is on my radar, but the good news is that I am about to info dump as much as I can about how I got from measuring this needle to this design. So hopefully, if you really wanted to, you could retrace my steps with a different needle of your choosing as a starting point. Okay, so I keep saying I designed a knitting machine, but that's slightly misleading. I actually kind of designed 3 knitting machines and a half, or maybe 6, depending on how you count. I took an iterative approach to this project, which basically means that I plan to start by producing something kind of basic but functional, which I could progressively refine and add more features to in short development cycles. This would allow me to build and test things in smaller chunks, identify and fix problems while they were still small, learn from those mistakes, and adjust my plan accordingly as I went. Thanks to a little something called hubris, I quickly learned that my initial idea of kinda basic was still wildly ambitious. My very first fuck around and find out phase, which I'm now referring to as Mark 0, was a huge mess that I couldn't even properly test because I did not nail down the fundamentals first. But we'll get back to that. An important thing to keep in mind is that a knitting machine is not so much one big thing as it is a system of smaller interacting separate subsystems. In my scheme, the main subsystems are the bed and the carriage. They are separate, but they do need to speak the same language. The carriage's main job is to house the cams, which are the bits of internal landscape that create a path to guide the needles in and out as the carriage passes back and forth across them. It also feeds the yarn to the needles at the appropriate time and place. The needle bed houses and stabilizes the needles in these narrow slots. The distance between the slots is the pitch, which, as we talked about earlier, is one of the main factors that influences the gauge of the knitted fabric and the range of yarns that can be used on the machine. Most commercially available domestic knitting machines come in standard, mid, or bulky gauge, which often, but not always, corresponds to pitches of 4.5, 6.5, or 9 millimeters, respectively. These tend to be distinct separate systems, with different needle dimensions optimized for a somewhat narrow range of yarns, paired with a complementary pitch. There are a couple of examples of convertible machines out there where you can use the same carriage with different needle beds of different pitches, like the KX360, but it's not common. And I know that this is likely a side effect of the specificity of those needles. In other words, if we think of our design as a drawing in a 2D coordinate system, then changes along this y-axis definitely affect the rest of the system, including the carriage design. But I also kind of assumed that changing the pitch, changes on the x-axis, would also demand some changes to the carriage design. And then I actually stopped and thought about it, and I realized the x-axis does represent the distance between the needles in the needle bed, yes. But from another perspective, it also represents how those needles change their Y position over time. And if I've learned anything since March 2020, it's that time is fake. As far as the needles are concerned, the time is always now. They don't know where they're going, only God knows where they've been, and they don't care how objectively long it takes to get between those 2 points, as long as they manage to meet up with the right friends along the way. So at least at this stage of development, when it comes to the relationship between the needles and the cams, the machine can't really tell the difference between putting the needles a little further apart and just moving the carriage a little bit slower. So that means, at least for now, I can develop multiple needle beds with different pitches and multiple carriage designs that can be interchanged at will, as long as I don't mess with the distance between major landmarks on the needles sliding in and out direction. Of course, I might need to rethink that a bit later if I wanted to add features that require more explicit timing, like mechanical needle selection, for example. In that case, the actual clock time still might not matter that much, and probably wouldn't have to impact the cams, but the carriage would probably need to be geared literally to a specific pitch. So a particular carriage would no longer be compatible with both 4.5 millimeter and 6.5 millimeter beds like I have now. Anyway, this idea of interoperability was really important for me. Some of these parts do take a long time to print, not to mention the material that goes into them, and I didn't want otherwise functional components to be rendered obsolete just because I made some tweak or upgrade elsewhere. I wasn't 100% perfect at this, and at some point, I'm sure there will probably be some necessary improvement that breaks backward compatibility, but so far I've been able to make 3 major versions of the carriage without having to junk my older needle beds, even as I've continued to iterate on the needle beds themselves. Right, so the needles are the center of the universe as far as this design is concerned, which is why I spent so much time rambling about them right off the bat. Before I could start modeling anything in 3D or even really in 2D, I had to get a really solid handle on a single dimension. How much action do these needles need in and out in order to do their job? The needle butt is the part that gets pushed around by the cams, while the hook and the latch are going to interact with the yarn. This extra leggy bit at the back varies quite a lot from model to model. For example, the LK150 needles have a very stubby little leg, while the needles I'm using have a pretty long leg. I think on the machine this was originally designed for, perhaps that leg plays a role in needle selection, but I'm not 100% sure about that, so don't quote me. Either way, it doesn't have a direct role in the design we're creating here, except that we do have to make some room for it, and we need to try to keep it from getting in the way. Sometimes we'll knit something that has fewer stitches than the number of needles available, so we probably want a spot for needles to hang out when they're not on duty. These needles won't have any stitches hanging on them, and we just want them out of the way, so we'll make space for these all the way at the back. There will be a hard stop here where the legs are contained under a cover. Okay, what's at the other end? Most knitting machines have some kind of sponge strip across the width of the bed that keeps the needles from rattling and twisting and slip-sliding around. Basically, you want a bit of gentle dampening pressure so they can move in response to the cams, but otherwise be pretty static. We're also going to want some kind of track or rails to keep the carriage aligned, so we may as well combine the sponge strip with the front rail component since they'll both impose a barrier on how far the needle can go. And from this out of work position, we can see that the furthest forward we should really put the front edge of that combo is just behind the latch pivot point. Any further in that direction and we start to get caught on the hook. Now, in theory, the width of this sponge rail component could be whatever my little creative heart desires, but in practice, I was once again constrained by the dull reality of material objects, aka the things available at my local and some not so local hardware stores. I decided to fasten this rail in place with screws. We do want to be able to remove it for maintenance and servicing, and I couldn't really come up with a better non-permanent way to keep it in place. This choice to use screws has perhaps come to bite me in the ass a little bit, which I'll discuss more later, but for now, suffice to say that it had to be at least wide enough to accommodate those screws, or whatever I would be misappropriating to use as a sponge strip, whichever was greater. In the end, I settled on 12 millimeters for the width of this part. Okay, so now we have a well-defined open working area where the needle butt can slide around between those two hard barriers. We've already got space set aside for an out-of-work zone at the back, but sometimes we'll also want a little break area for needles that are in work on the project but temporarily on hold, like when we're knitting short rows, for example. While in hold position, the needles will have stitches hanging on them, but we want the carriage to just ignore them the next time it passes. We'll make space for these all the way at the front of the working area. Strictly speaking, neither the out-of-work nor hold positions are necessary for knitting, like if you only wanted to knit fixed with rectangles of stockinette, but leaving them out would pretty severely limit what the machine can do, so I want both of them. We'll add in a tiny bit of a buffer to each of those zones to account for a little bit of wiggle room so the needle butts aren't just like super squeezed in there. And we'll also account for a couple of millimeters for a little physical barrier between the zones, like a little railing that will keep them in the proper lane once they start interacting with the cams. And by the way, that 2 millimeters for the barrier width isn't super duper scientific. It's just based off of my best estimate of how thin I can get away with printing that part out of PLA before it becomes too fragile to function. Everything in between those barriers is going to be the space that we actually have to slide the needle butt around and finally knit a stitch. In its home position, the needle's hook should be just about at the front edge of the bed where the live stitches can comfortably dangle. But we don't actually know where that front edge is yet. What else do we know about that hook position that can help us work backward to figure that out? Well, we know that it has to come as far forward as it can to free the latch from under the live stitch and grab the new yarn, which, by the way, we're going to drop right about at this little hinge point between the latch and the needle. So if the needle is as far forward as it can go before running into our hold zone barrier, then we want to make sure the stitch, and therefore the front edge of the needle bed, is at least far enough back to be clear of the latch. The rest of this working space is how much room the needle has to pull the new loop of yarn through the old one, aka the range we have to adjust the tension. Boom. We have unlocked our first dimension. I mentioned earlier that I had an ill-fated early attempt at all this, which luckily failed pretty fast and pretty early. I'm not going to go into a ton of detail about that design because I cannot emphasize enough how much it did not work for very stupid reasons, but I think it might be helpful to talk about what went wrong in my process and how that informed the way I ultimately planned the rest of the project. Basically, I worked out a bunch of the stuff I just described about needle positions, and I got pretty excited and jumped into 3D modeling and printing a little prototype of a tiny little section of needle bed. The needle bed seemed to do everything it needed to do. It held the needles in place, they could slide around, and I could hand manipulate them to manually knit stitches. Easy, great, time to move on to the carriage. I knew that a few of my goals needed a way to kind of do conditional knitting in different positions, where you can flip a lever to control whether stuff gets pushed into the main knitting path or diverted into a standby position. And I had a bunch of ideas about how to implement that, so I worked out sort of the basic path that the needles would have to take through the cams, and then I started adapting it to accommodate these alternate paths. Things looked pretty promising when I simulated the movements of parts on screen, so I started printing and assembling components for the fancy spring-loaded cam system. There were a lot of actually pretty solid ideas in it that I eventually did circle back to, so this is not the part that I f***ed up, I might have made mistakes here, but we'll never know for sure because I couldn't actually even test this design. No. The f*** up is that the different parts of the system, despite seeming to do the right things independently, couldn't work together. I got so excited about designing in 2 and 3 dimensions that at no point in the process did I double check that these all-important single-dimension measurements were applied in the same way in both subsystems, and I hadn't organized my code in a way that would enforce consistent measurements or even make it obvious when there was a conflict like this. Even though I didn't get a working prototype out of it, this time was still really valuable for experimenting with the software, with the 3D printer, and with the materials. I could probably have salvaged this design by making a few changes to the layout and just moved forward from there, but this experience made me realize a couple of really important things about my overall process. First, my code and technical drawings both kinda sucked. I was sort of winging it at this point, so the documents were really disorganized and the models were hard to change, and I just hadn't been doing good version control up to that point either. I decided to scrap what I had and start writing and drawing again from scratch, this time with a much more intentional plan for how to structure the project based on what I had learned. I begrudgingly had to finally look up what a Gantt chart is for this, and I am furious to report that it was actually very useful. Second, if you've ever debugged code, tried to sew a pair of pants that fit, or had back pain, you probably know that the place where a problem becomes noticeable is not necessarily the same place you need to look to fix the problem. So even though the complexity of the cams was not the root cause in this case, and this particular issue was embarrassingly easy to spot once you see the whole system together, the sheer amount of stuff that could go wrong here might have made it very difficult to identify the source of a more subtle error. Like literally too many moving parts. I realized that debugging advanced features could prove to be an absolute nightmare if I didn't take the time to test and confirm my most basic assumptions about how the fundamental essential components would interact with each other. So instead of trying to design a machine that could knit the stuff I wanted to knit, I decided to start again with the bare minimum machine that I thought would knit at all. I told you. Get that working reliably, and iterate on capabilities from there. So far, you've seen me scribbling on graph paper and sliding needles around on a table, which I found super helpful early on to wrap my head around how this whole thing could work. There can be a lot of advantages to working digitally, but at this sort of spatial conceptualization stage, I often find it really helpful to be able to just get my hands on things. Whether it's making handwritten notes, sketching with a pencil, or building little models out of paper and hot glue and wooden skewers. But if I want to 3D print this machine, I do eventually need to fire up a computer and create some models in software. So, which software should I choose? For the 3D side of things, I decided on OpenSCAD. What appealed to me about this application was it's free and open source, which is always nice. It's script-based, so you generate your models by writing code rather than in a graphical user interface. For me, this allowed me to pretty seamlessly apply a bunch of the transferable skills that I'd learned from programming 2D and 3D graphics and processing. So I was able to hit the ground running instead of facing the learning curve of a totally new interface in a graphical CAD software like Fusion 360. Writing code to define the shapes also has a couple of other nice perks, like making it really easy to repeat or reuse things in multiple places, or to change a value in one place and have it everywhere that relies on that variable update automatically. I also really like that I can use a version control software called Git to track and view the changes I've made to the files over time in a really clear line-by-line way. And I can try out a bunch of different things in a non-destructive way by using Git branches. OpenSCAD isn't perfect for everything, though. For example, it may not be the easiest or most intuitive option if you need to create more organic or flowing shapes, or even for some common design features like rounded corners or edge chamfers. The way you construct most of your more complex shapes is based on Boolean operations: unite, intersect, or difference being the main ones. So I start with a simple shape like a cube, and I modify it with another shape. I can use that second shape to add to the cube, or I can throw away all of the parts of the two shapes that don't overlap, or I can use the second shape to take a bite out of the cube. You might already have encountered this sort of thing as a kind of a side option in other places, like in vector graphics programs or somewhere like Blender, but it's really kind of the main course here. Speaking of vector graphics, there were a few curvy shapes like the cams that I knew were going to be kind of a pain to model from scratch in OpenSCAD, so I decided to draw them and lay them out somewhere else first, and then save those shapes as SVGs that could be imported into OpenSCAD for 3D extrusion. I chose Adobe Illustrator for my 2D technical drawings, even though it's decidedly not free or open source, because I was already very familiar with it from other projects and I was already paying for it. In the long run, though, I definitely think it would be more accessible not to have those design documents locked into a proprietary format, so I'm working on cleaning that up now that I'm no longer under deadline constraints. For the first basic iteration, Mark 1, if you will, I just wanted to focus on making sure that the bare bones essentials were present and functional before moving on to anything ambitious. My previous misadventures had already given me some pretty good insight into which parts of the machine were not really optional versus what I could probably noodle on later. So the Mark 1 iteration was about building out the absolutely essential core anatomy. A lot of this is stuff that I hoped would stay fairly constant and not change much throughout future iterations, especially the needle bed and outer shell of the carriage. So first, of course, we have the needles. Each one of these fits into a slot in its own unit, which is laid out according to all of those measurements we established earlier, and the overall width is determined by our desired pitch. For Mark 1, I started with a typical mid-gauge pitch, 6.5 millimeters, because I was pretty confident that this size would produce comfortably printable parts. I figured that the smaller I go, the more risk there is of running into the sort of muddy complications that I was hoping to strip away at this stage, so I saved experimenting with the standard gauge for later. In the working area of the bed, the needle slot is going to be just wide enough to accommodate the needle, plus a little bit of tolerance. The needles should be able to move smoothly in this slot, but we don't want too much extra room for them to kind of flop around. They should stay pretty stable, upright, and aligned with the y-axis. Toward the front of the bed, though, I want to make the slots a little bit wider because when the needle grabs a loop of yarn, it'll have to pull it back into this space. So it's got to be wide enough for at least a double thickness of yarn plus the hook. In between those areas, we're left with these little walls, what I've referred to as the comb. On more advanced machines, you'd usually find gate pegs here. Having some kind of physical barrier here between the stitches helps knock the old stitch off the loop when the needle retracts rather than letting it try to come along for the ride, and helps distribute the tension evenly between neighboring stitches. So that's the basic needle unit. We can pack a bunch of these individual needle units next to each other to form a needle bed. In theory, the needle bed can be any number of needles wide that you want, but in practice, I had to limit myself to what would fit within my 3D printer's printable area. So to extend our total number of needles, we'll make it so each of these individual needle beds can connect together into one long working surface. Each of those needle beds also needs a back cover piece, and we'll pop the back carriage alignment rail right about in the middle of that. And we'll need that sponge bar cover and front rail that I talked about before too. These components will scale in width to match however many needles we put in the needle bed. At either end of our array of connected needle beds, we need a spot for the carriage to start or end its journey. Not only is this a handy place to park the carriage when it's not active, it also supports the leading and trailing edges of the carriage to keep the whole situation aligned over the edgemost needles. Kind of like how a table saw or a quilter's sewing machine usually has a bunch of extra surface area to prevent the work from twisting under gravity. These carriage rests will have the same type of connector so they can attach to any of the needle beds, and they'll also have rails in the same position as on the rest of the bed. Now let's consider how we're going to push the needles around. I want to make this part virtually foolproof, with no sneaky little spots where the needles could get stuck or run into anything or go the wrong way. So I'm going to find all the major landmarks of the needle's action cycle, spread those points out a bit, and draw a nice smooth groove that will guide the working needles from either side exactly where they need to go at every step of the way. The out-of-work needles at the back also need their own path, and the needles in hold position at the front need one too. And I'm going to angle or wedge the entry points for each of these paths a little bit. That way, as long as the needles are more or less in the right zone, they'll still be funneled toward the correct path, even if they're not 100% perfectly aligned to start out. I also want to think about where the needles will exit the carriage. Ideally, I want this path to spit them out at the same height they came in, so that the butts are properly aligned for the return pass. Once I'd figured out the path for one side, I mirrored it over to the other side so that the carriage could knit in both directions. The overall width of the carriage is somewhat flexible. Once again, a major constraint here is the maximum width of my printable area. But another consideration is the slope of this little roller coaster cam. Too steep and the needles will really struggle and potentially even damage the plastic. But ideally, I don't want to make it a lot bigger than it needs to be, since larger objects take longer to print and use more material. I didn't really come up with a hard and fast rule about angles here. As I said, I'm not an engineer, so my approach to this was much more of an intuitive eyeballing rather than something informed by any particular understanding of the physics. But I will note that anecdotally, abrupt changes in the direction of the needle travel seem to be much more of a concern than angles of individual slopes within reason. This point at the peak of the roller coaster determines how far back the needle retracts, and thus how loose the stitch will be. Longer retraction equals longer loop of yarn. I know from all my needle measurement extrapolation that I have a certain amount of potential range to adjust the tension, but at this point I'm not totally sure yet how much of that range will actually be useful. I decided to make this variable section of the cams separate from the main cam plate component so that I could swap out different sized tension peaks without having to reprint the whole base each time. These pieces will attach with little screws. There's one more section of the carriage that still needs to be designed, but before we get too swept up in the excitement of it all, this is a handy check-in point to test whether the needle bed and carriage components we have so far actually work together the way we expect them to. Up until this point, I'd been step-by-step testing individual components, although I've been breezing past it a bit in the retelling, for kind of static stuff like, are these parts the right size? Do they fit together? Are they easy to print? And so on. And after the Mark Zero debacle, I made sure to write code for my models that would allow me to visualize how the entire assembly would fit together in 3D. But this is really the first point where it starts to come together as a moving machine, subject to forces like gravity, inertia, and friction. So at this point, what I want to know is, can the carriage slide over the bed easily, or do harsh edges and corners catch on each other? Do the cams move the needles or not in the way we expected in all three positions, and so on. I ended up making a few changes at this point, like making the rails on the needle bed a tiny bit taller than the depth of the corresponding slots on the carriage. This means that most surfaces of the carriage are actually hovering a little bit above the surface of the bed, reducing the overall friction. And over the course of several iterations, I gradually replaced a lot of sharp corners and edges with rounded surfaces that would glide more smoothly over awkward transition points like where the needle beds connect. Otherwise, the cams seem to be doing their job as expected. But to confirm that, it was time to work on all of the carriage business that happens out in front of the needle bed. We, of course, need some way to guide the yarn to the right place where the needle hooks will be able to catch it. We already worked out the y coordinate for this with our needle calculation, and for the x coordinate, it makes sense to just put it at the center of the cam plate to maintain the symmetry there. So now we need to consider the Z height. Hey, there's that third dimension. Yes, I am Canadian. If we put the yarn feeder too high, the hooks won't be able to catch yarn at all, or they might only be able to catch part of the strand and you'll end up with a bunch of split stitches. If we move it too low, the hooks will get caught on it, which could jam the machine or damage the needles. So we're looking for this Goldilocks spot where it just skims past the height of the tip of the hook. To further reduce any chance of unwanted collisions, I made this feeder part funnel-shaped. So it only dips that low in a really limited area where it's needed, and the rest of this underside has plenty of headroom for the needles to move around without risk of catching on anything. We're getting there, but we still need at least one more thing to make sure the stitches are formed correctly. As is, the needle latches will have a hard time clearing the existing stitches when they push forward, especially if the stitches are snug, because the fabric sometimes wants to just come along for the ride. We need something to hold the fabric back close to the needle bed and provide some resistance so the needles can push through. In my code, I refer to this part as a stripper plate, as in it strips the fabric off the hooks as it passes, but I actually don't think this is a very good or descriptive name in retrospect. I think I half remembered that passive machines have a special mechanism called a stripper, and other machines have something called a sinker plate, and this isn't quite either of those things. The Bond machines have a part with a very similar function, which is called a fabric guide, so I might just go with that for familiarity's sake. Anyway, like the yarn feeder, finding the right shape and position for this is a little bit of a balancing act. We want it to hold the fabric back, but you can't squeeze it too much against the needle bed or it'll drag and cause problems, and we need to allow for a range of yarn thicknesses as well. I solved this by actually angling the front edge of the needle bed under, which gives the fabric a bit of extra backwards room to breathe while still allowing the fabric guide to push it far enough back for the latches to clear. I also slightly angled the inside surface of the plates and positioned them at a height so that they would support and slightly lift the needles at the far end of their range. I'm not actually super sure if this is contributing much, to be honest. All the free edges need to be rounded over and angles softened so they don't catch on the needles or the fabric. And finally, I split this into two pieces with a teeny little gap between them to make it possible to change yarn colors without needing to cut the strand. So this whole nose piece situation, which I called the yarn carrier, but later learned should maybe be called the fairing, attaches to the front of the cam housing. We can add a little wire loop to guide the yarn from the back, and then, hey, I think we have a minimum viable carriage assembly. Now, if you watched my earlier video about knitting on the circular sock machine, you might recall that this symmetrical needle path is really simple to design and understand, but it does require some annoying concessions from the knitter. You have fewer cast-on options, and it's a lot more prone to dropping stitches during some tasks if you don't take precautions and pay super close attention. So this is definitely more basic than I ultimately want, but as long as you keep those little gotchas in mind, Mark I is a reasonably serviceable little knitting machine. But I was pretty sure I could overcome those pitfalls by thinking about the cam design in a whole new way. So something that's helpful to keep in mind when we're redesigning our cams is that as long as our sponge strip is working as intended, the needle butts are going to pretty much stay wherever they are until something comes and pushes on them. And when that something stops pushing on them, they'll stay at this new position until something else comes along to move them. I had to keep reminding myself of this because the way I was sort of manually simulating these interactions in my 2D drawings, it was really tempting to think of it like the needles were actively moving through a static cam landscape, like they were a little car or a rolling marble that would have a certain amount of inertia to sort of carry them further in whatever heading they're traveling, even after they've lost contact with the cams. But what's actually happening, of course, is that the needles are passively minding their own business in their little slots, and the carriage is passing over them, sometimes nudging them up or down, but otherwise the needles shouldn't have too much momentum of their own. That means that they don't have to be in constant contact with the cams in order to stay in their lane, only when we want them to change position. And that means we can start exploring a more open floor plan that would allow for a little bit of asymmetrical movement. And that means we can eliminate that first needle retraction, which is totally superfluous and a huge pain in the ass. It's only there because we need it there on the other side. So when the needle enters the carriage, it'll run into the bottom edge of this cam, and it'll ride that edge all the way down to the forward position. By the time it reaches the center of the carriage, the latch will have cleared the old stitch and will be in the zone to grab the incoming yarn. Just before the center of the carriage, we'll give the needle a little nudge back up so it's high enough to catch the upper edge of the cam on the other side. This time, the cam will be pushing the needle back, retracting into the needle bed and pulling the new loop through. So the position of this peak will help control the stitch length. After cresting that peak, the needle will sail along until it bumps into this little sloped ceiling, which it will ride until exiting the carriage at the perfect position to set up for the next row. We can even make the tension adjustable by adding a pivot to the pointed end of these cams, and a curved slot in the cam plate under the large end to add an adjustment screw. So this modification achieves a few exciting things. First, the tension cams are smaller, which means they can be printed faster and use less material. Plus, you get a whole range of tensions out of a single pair of small cams that are adjustable in place, instead of having to print multiple discrete cams that need to be fully removed and replaced each time you want to change the tension. Second, because we've now eliminated the redundant needle retraction, we can work a lot more comfortably with techniques that put the needles in forward positions. For example, if I had needles in the hold position and wanted to return them to work, with the previous cams, I would have had to go through and manually tuck all the latches back under the live stitches to avoid dropping them. But with the Mark II cams, I can simply push all the needles back into half knit or forward working position and resume knitting. This also makes it possible to knit intarsia designs, where the yarns are laid across the bed by hand rather than fed through the carriage. So that makes this iteration, I think, a pretty significant step up from Mark I in terms of capabilities, with a few relatively small changes to the design. I've got something pretty useful and versatile without wading too deep into the complexity and headaches of moving parts. Honestly, if you're interested in building one of these machines, this is the version I'd recommend right now. But there were still a few things I wanted a machine to do, and I had a few ideas to try out. A machine feature that would open up a bunch of possibilities in terms of both knitting techniques and laying the foundation for future development is what I've been thinking of as conditional knitting. If a switch is flipped and a needle is in a certain position, the stitch will be skipped, else the stitch will knit. This feature is pretty key for knitting stranded colorwork designs, for example, and I think it'll also be essential for eventually being able to do tubular knitting and ribbed patterns if I'm able to develop a double bed configuration down the road. So what we need to do here is take our one big working zone and split it into two zones, but only some of the time. Sometimes we'll want the machine to behave just like the Mark II, funneling all the working needles into this knit path along the underside of the tension cam. But sometimes when we're knitting our fancy techniques, we only want selected needles to knit, and we want to redirect these unselected needles into a different path where they'll miss the tension cam, the equivalent of slipping those stitches if you were knitting by hand. In both cases, we probably want all of those needles to exit the carriage together in their usual place, all lined up in the home position. So what we need is a little gate at the entrance to the new path, which can be closed when we don't need to slip stitches and opened when we do. But let's not forget that the entrance to the slip path also has to double as a universal exit in the other direction. That's no problem if both gates are open, but if we want to block off the slip path, then we need to somehow rig the cams to act as a one-way gate. I mean, I guess we could rely on the operator to remember to change the cam position in between every single row, but like, come on. It just seems rude. So when it came to mechanism, I was inspired by Steve Turner's use of torsion springs on the up-throw cams of his circular sock machine. It's a slightly different application in that case, but I thought something similar might work here. Now, I mentioned in my introduction video that I was hoping to stick to tools and materials that would be relatively accessible and widely available. The problem here is that torsion springs are kind of a niche hardware item. Like, yeah, you can order them online, which, at least where I live, probably involves paying several times the cost of the item in shipping fees, but I can't just stroll into a local store and pick up a few of them to try. Or can I? Okay, so stripping hair accessories for parts is probably not the ideal solution in the long run for a lot of reasons, and I'm going to dissect a couple of those reasons in a moment because they're a pretty big part of why I can't really wholeheartedly recommend the Mark III as a stable build yet. But this did give me a quick and cheap way to experiment with the mechanics of what I was trying to do. The idea is that one leg of the spring fits into the cam plate, the other leg of the spring fits into the bottom of the cam, and the whole assembly is kept in alignment with this little rivet or pin or what's it that was holding the spring in the hair clip. The exiting needles can push past the cam and it'll spring back into place when they're done. The good news is that the concept does mostly work, but there are a few pretty serious implementation bugs that I need to work out, so I expect a few of these details to change. In addition to the spring mechanism, this whole part should be able to pivot, much like the tension cam. We have a little disc cut out of the cam plate where the spring and the cam are attached, and it's got a little stepped profile to keep it from falling through. On the other side of the cam plate, we attach another slightly larger disc, and on this side we have a couple of attachment points to insert a lever. Now we have this little captive section that we can pivot around as needed to reposition this sprung cam. But of course, unlike the tension cams, we don't need a continuous range of positions here. In this case, we need to actually lock into one of two states, open or closed. Plus, switching between these states is an operation that the knitter is likely to do frequently while knitting through a pattern, so ideally we need a solution to hold this in place that doesn't involve a screwdriver. I once again raided the back of my head for inspiration. This bobby pin has a bit of memory to it, so it's flexible enough that I can press it down to free it, but when it reaches one of these notches, it wants to spring back up to its resting state, and it'll stay secure there until I intentionally manipulate it again. So I'm really proud that I got something working here, but I'll admit there's a lot going on in this assembly that I don't love. Or, I mean, there's a lot of good raw material in the ideas, but how it all comes together still feels a lot like a first draft to me. For one thing, it's really finicky to build. I added registration marks in a few key places, but I still wouldn't say it's easy to align the parts correctly. Second, it's not very durable or reliable. This is partly because I leaned pretty heavily on super glue to attach some of the pieces of the prototype, partly because some of the pieces are small and awkwardly placed, and partly to do with the hardware. So I think there's a lot of opportunity to rethink those elements of the design with longevity in mind. Another spot that could use another look is right here where the needles exit the cam path. They're supposed to return to this home working position, and on paper, or on vector drawing, it seems like that's what they should do. But in practice, they often end up too far back, where they can get jammed on the point of the gate cam as they re-enter on the next pass. I compensated for this while knitting by just quickly running my finger along the line of needle butts between each row, but that's an extra step that we really shouldn't need to do. What I didn't anticipate in my sketch simulation is how much the force in these spring-loaded gate cams would affect the final position of the needles. When the needles push past that gate, the gate doesn't sit passively open for them. It's pushing back, and unlike the other cams, it's moving and putting some stored energy into that push. So I think I need to tinker with this point to get a bit more control back. I've also logged a few issues that resulted from my choice to scavenge the spring parts rather than buy something off the shelf. First, to mirror the layout across the cam plate, I need both left-hand and right-hand wound torsion springs. Typically, a pack of hair clips would contain one or the other, but not both. So now I've got to find two styles of clips that use similarly sized springs, but wound in opposite directions. This didn't take me long at the store where I could compare them in person, but it definitely did complicate things. Second, because I used springs from 2 different styles from different manufacturers, my left and right springs weren't otherwise identical. I ended up with springs that don't quite have the same deflection angle, and they probably don't have the same torque. The latter is whatever. I wasn't specifically factoring in the torque into anything for this, though it would potentially be useful information. But the deflection angle definitely does affect the final position of the cam, so I had to compensate for that on one side. Again, not an insurmountable problem for the prototype, but maybe a problem that I could avoid passing on to future makers. Third, because these aren't picked from a parts catalog components, it's hard for me to tell you what to buy. Like, I can describe what I ended up with and give you some tips on what to look for, but that's not the same as being able to provide a part number or specifications that would be likely to replicate my results. Fourth, I don't like that this is pretty wasteful. I have hung on to the extra bits of the clips that I took apart, but I don't know what kind of plastic those pieces are made out of, so that does sort of limit the ways that I might be able to reuse or repurpose them in the future, since I don't know if they'd be safe to melt down and turn into something else. Finally, I reused this little rivet guy from the hair clips, but it is not up to the job I need it to do for the long term, which is to provide a straight and stable axis through the pivot point of the cam. It's hollow and the metal is super soft and it deforms too easily when the needles push the cam open, and eventually the cam just gets twisted out of position and it starts to jam on the needle bed. It's not great. So yeah, I do consider the Mark III to be a successful proof of concept. I've been able to knit projects on it, but there's a lot of stuff I need to overhaul before I would encourage others to build a version for themselves. So what's next? Well, there's a bunch of stuff this machine can't yet do that I'd love to work on, but I think the first order of business is to fix a few existing problems. I just described a bunch of issues with the Mark III cam system that need work, of course, and there's also a couple of areas in the needle beds that I think need attention before moving on to fun new features. I mentioned earlier that I wasn't satisfied with my choice to use screws to attach the front rail, and that's because it interrupts the sponge strip. This means that the needles closest to the screw holes don't necessarily get enough cushioning, which makes them more prone to slipping and moving in unexpected ways. For example, I've run into occasional jams when a needle kind of tips forward and the very back of its leg ends up too high to slide under the back cover. I'm almost certain that this is only happening to the needles with dodgy sponge pressure, so if I can even that out, it should make for better knitting on all models. I'm also hoping that resolving this issue now will help future-proof things a bit for when I want to eventually start working on a ribber, since the pressure from the sponge strip will be extra important when I'm also battling gravity. There's also a few peripheral accessories that I think would improve the knitting experience. I haven't got around to adding a row counter yet, but I think that would be a nice and hopefully easy upgrade. I haven't yet figured out the best way to use a yarn mast with this system either, so I've been managing my yarn by hand, but I'd like to work that out because I think a lot of people would appreciate it. And I always assumed that I would add a handle to the carriage, but then I couldn't decide on the placement, so I kept putting it off. I haven't really missed it, but I feel like other people might. I know there's been some interest already in a bulky gauge machine, so I might eventually try to adapt this design for different needles, or at least see if I can make it easier for others to customize the project in that way. Long term, I really do want to come up with a double bed design. Hand manipulating knitting is super time consuming, and tubular knitting isn't even possible on a single bed, so this would really expand the range of what the system can do. I've done a few quick preliminary sketches, and I'm fairly confident that it's possible. I'm just not sure that I'll be able to maintain backwards compatibility with the parts I've already got. Like, I think a lot of the same design logic would still apply, but getting the beds to face off with the correct alignment might just demand some breaking changes. I am not 100% sure if it'll be possible to make it an upgrade that you could add to an existing machine. It might have to become a whole separate system. We'll see. In the very long term, I think it would be really cool to experiment with different ways of transmitting, storing, and even manipulating needle selection data, both as a useful feature and as an interesting technical challenge. So friends, that's how I got from an idea to where we are now, and where I hope to go from here. I know this is a ton of information, but I'm sure I still left stuff out. There's some topics I still plan to cover in upcoming videos, including a walkthrough of the code for anyone who might want to tinker with it, and how to print and assemble and set up the machine. I'll also announce when the code and STL files are ready to download, which should be alongside one of those videos. So if you're not already subscribed, now's a great time to do it if you're interested in following this project. Until then, stay curious.